Okay, let's get started with class for today. We're gonna pick up where we left off on Monday. Does anyone need the notes at all? I handed out like the 7.3 applications of SVD. Yeah, so there's a little bit more theory I want to go into before going into. I showed you some Python code, but it was only the first portion of the Python code where I was looking at, I guess, like the correlation matrices and the data itself. And so we're going to go a little bit more into the theory here to show like how SVD is applying to these data matrices that we're looking at. And then I'll look at the Python example, and then we'll look at some other examples as well. And so what we did in class on Monday regarding the section 7.3 stuff is we saw that pretty much all these data tables that you can have on Excel or something like that can be interpreted as some sort of matrix. Usually they're going to have a lot of rows and maybe they won't have as many columns, but so like the columns correspond to some sort of variable or quality that you're measuring, and every single row is an example or like an instance of the thing that you're trying to measure. So on the first page, it's a bunch of flowers. Every single row corresponds to a single flower, and then every single column is some sort of variable or measurement corresponding to that flower. So you can view this as some sort of matrix. And so whatever you can do in linear algebra with matrices, you can apply to these sorts of tables as well. And so we were concerned with looking at correlation and how to find correlation, which is really how two variables relate to one another, or two or more variables relate to one another. And it has this pretty complicated looking formula that eventually we interpreted in terms of the dot product. So you can take this formula and you can interpret everything in terms of vectors. And in doing so, you can reduce it down to just a dot product of these two vectors divided by the product of their magnitudes. So this is like mean centered in the sense that you take your instances, like your measurement, and you subtract by whatever the mean of that measurement is. So you're thinking in terms of columns when you're doing these means. And so you interpret everything in terms of vectors, and then from vectors, you go to matrices, and from dot products, you go to matrix multiplication. So and understanding that we're really just doing dot products at the end of the day, you can expand all these ideas to interpreting things in terms of matrix multiplication. So where we left off is we saw that this matrix product X transpose times X is going to end up encoding all of the pairwise covariances, assuming the columns are mean centered as we have been doing, and then you divide by n-1, which is like the length. And so the ijth entry of this X of t times X in the covariance matrix is this dot product that we have above. Maybe divided by some things, but at the end of the day, you get this for your covariance matrix, right? And then we also have correlation matrices as well, but this is just taking the covariance matrix and then normalizing it so that all the values are between -1 and 1. So it kind of gives you the same information, but it's more convenient to read things off in this way. But we're just going to focus on C, the covariance matrix. I talked a little bit about what principal component analysis does, like what the big idea is. And I think another way of thinking about principal component analysis that I didn't say already is this is like one of the strongest techniques that we have, or that people use when doing dimension reduction. That's kind of the name of the game with principal component analysis. So it's dimension reduction, as we'll see in a couple of examples here. So it's really just taking information or data that can have like 100, 1,000, 10,000 dimensions to it. And then you're really just looking and restricting the dimensions, so that way you're only considering what depends on the example, but maybe like 5 dimensions or 5 main components. So it's taking something that could have a lot of dimensions and reducing it down to something that has significantly less. And there are advantages to this. Like you can look at something that's 9-dimensional and reduce it to maybe something that's 1 or 2-dimensional. If you have something that's 1 or 2-dimensional, you know how to like draw pictures around it. You know how to visualize it in ways that are a lot more sophisticated. So we don't know how to view things in 9 dimensions, obviously. And so this is what these kind of pictures represent here. I think I was talking particularly about like cryptocurrencies, and I was saying like if you have only one relevant component, that's kind of what this plot is saying. So each of these points here correspond to an eigenvalue. And this is saying that and I guess the height that they have or the altitude they have in this plot is illustrating how influential that eigenvalue is actually going to end up being. So if you have a plot like this describing the eigenvalues, this is really saying that in order to understand your data, you really just have to understand the single eigenvector corresponding to this eigenvalue, and you wouldn't really be losing that much information. If you look at this picture instead, it's saying there's 3 influential eigenvalues / eigenvectors that tell you information about the data, and nothing else really matters. So it allows you to distill your vision to what's important, pretty much. And so the purpose of PCA is to find a set of basis vectors for a data set that point in the direction that maximizes covariation across the variables. So we're thinking like the more variance, the greater the amount of relevance that you have. So you're kind of like redefining your coordinate axes so that way they maximize the variance in a sense. So I'll say more about this later on. But just the set notation. So we're going to imagine that we have an n-dimensional data set existing in like an n-dimensional space with each data point being a coordinate in that space. This is just setting terminology and notation. So it's sensible when you think about storing data in a matrix where you have n observations and m features. So the data is going to live in Rm and comprise of n vectors or coordinates. This next paragraph I kind of said out loud already. So PCA is about maximizing the amount of variance that you have across the variables. And so how does this actually come into play? So this is like the theory part, these next 2 examples, and then I'll look at the Python that I started showing you, the Python code I started showing you in class on Monday. And so the goal here, well, for this example, we're letting X be our data matrix, and we're going to let W be a vector of weights. And so we want to be able to relate the solution to principal component analysis to the covariance matrix C. So what does it mean to relate the solution? Or what am I saying when I say like the solution to principal component analysis? So the main goal, what I'm getting at here, is we're going to have the following goal. Right, so we want to find, so when I'm talking about a solution to principal component analysis or PCA, we want to find a vector of weights W, so that's the W given to you, such that X times W is going to have maximal variance. That's the goal here. And maybe it sounds a little bit confusing at the moment. But the proof of this isn't going to be so bad. It's really like a 2-parter. Like this is really just setting up what we're going to be doing in the next part of the example. And so what we're going to do is we're going to let lambda be the following. So we're going to let lambda, so really we want to maximize like this something regarding like X times W. So we're going to let lambda be equal to the magnitude of X times W squared. And then this is kind of like a data analysis thing, but we're then going to scale the norm. Because you can have high variance just by having like huge numbers, pretty much. And so you don't want the variance to just be like we have huge numbers. So what we're going to do is we're going to scale the norm by dividing by the magnitude. And so we're going to scale the norm. This isn't really like a data science class, so I'm not going to go into too much detail about like the data and how to like make it a little bit nicer. But we're going to scale the norm in case W has huge numbers, because that could mess things up a little bit. And so what we end up having is the following. And this is kind of a calculation we've seen a couple of times at this point, or at least it will look similar to the things that we've done. So we have that lambda. We're saying this is equal to X times W squared, like this magnitude. And then we're dividing, so we're scaling via division by the magnitude of W in case the quantities or the numbers in W are too large. And so what we can do here is we can express this square as a dot product. So this is really X times W is just a vector. So you can view this norm or this magnitude squared as the dot product of XW with itself, which you can write in the following way. This is really XW transpose and then times XW. And then you can do the same with the denominator, where if you have the magnitude of W squared, it's just W dotted with itself. And then we can use what we know about the transpose. So this is equal to W transpose, X transpose times X transpose times W. And then we still have W transpose times W in the denominator. And so the point was I wanted to relate the solution to the principal component analysis to the covariance matrix C. And that's exactly what we have here. We have this X transpose times X. This is going to be equal to W transpose times C times W. Then you have W transpose times W. And so the goal, so we're not like done in terms of showing like how do we actually do principal component analysis, but at least we have that this lambda that we want to maximize relates to the covariance matrix that we've been looking at. And so really the goal here, if I were to put it in words, is we want to maximize now this. So we've seen something like this in the past, right? Where you do like some vector transpose times C times W, where this is like positive definite or something like that. That's kind of what we have here. This is called a quadratic form because you're going to have like W and then W over again. So you'll get a quadratic equation involving the variables or like the weights of W here. It's not really super important, but that's why I'm saying like I'm going to call this a quadratic form. Right, so that's the goal, is we want to maximize this numerator that we have. And again, this part didn't really matter all that much. It's something the book did, and it's something they care about in data science. But in terms of the linear algebra, what matters is we have the C in the numerator here. Any questions about this example, I guess? I wouldn't worry too much about like the data science stuff, but it's mostly like this part, like this equation. Any questions? Yeah, we've done plenty of calculations like it already, and this one's a little bit more tame in comparison. And so this next example is really just a continuation of what we were doing here. It wants you to finish the job. So it's asking, how do we find the W in the previous example? And so the idea is going to be, we're going to extend this single vector W into a matrix capital W. And then we're going to relate the principal component analysis to eigendecomposition, or relate this idea of diagonalization. And so the thinking is the following. So we have the thinking here. Maybe I don't have to write this down, but we're really considering, by looking at a capital W, like a matrix W instead of a vector W, we're really considering the entire set of solutions. Not just a vector. And so what this means, it's kind of like when we were doing projection in the past. There's like projection onto a line, and then there's projection onto like a column space, which might have more than one dimension. And so what we're going to do is we're going to take this equation and we're going to replace the vectors W with a matrix W, which is going to make some changes. So we're going to replace little w with the matrix capital W. And what this is going to change, it's going to change. So again, we can't divide by matrices, but we could multiply by inverses. So this is going to change W transpose C W over W transpose times W to the following. So instead of having this W transpose times W, this is just a number because it's really just a dot product. You can write this as being the following. So instead of having lambda as like a one-dimensional scalar, we're now going to have a diagonal matrix consisting of those scalars, which I'm going to call uppercase lambda. And then this is going to be equal to W transpose times W inverse times W transpose C W. So it kind of looks like projection a little bit, but not quite. So again, with this going from a vector to a matrix, this is really like multiplication by the inverse instead. And so what ends up happening here is you can rewrite this as being equal to W inverse. So you can distribute the -1 sign to both of these. And so this flips the order and applies the inverse. So you have W inverse multiplied by W. It's really the transpose inverse. I'm going to write this as W to the -t. So it's the inverse and the transpose. Some people use this notation. It's convenient, so I'm going to use it. And then you have C, W. And then implicit in this is we're assuming that W is an n by n, or it's like a square matrix. Otherwise, you wouldn't be able to do such a thing. And so what ends up happening is we have W inverse cancels out with W transfer, or I didn't cancel out the right thing. This like W transpose inverse cancels out with the W transpose. And so this ends up just being equal to W inverse CW. And I'm just gonna write it like this. So these things cancel out, you get W inverse CW, and then you have this is equal to lambda. And so now if I multiply on the left-hand side by W and the right-hand side by W inverse, we end up getting the following. So we end up getting that C is equal to W times lambda times W inverse. Right? And so this is going to give you a way of describing what W is going to be, right? This is just the diagonalization I can't spell today. Diagonalization of the covariance matrix C. At least that's the idea. I'm skipping some of the details, I suppose, but this is what matters is you get this equation right here. So principal component analysis, like finding the solutions for principal component analysis, which means maximizing the covariance, is really just obtained by taking your covariance matrix and then performing diagonalization. And then the various components are just going to correspond to the eigenvectors, right? So this matrix W is just going to be the eigenvectors of C, and then lambda is just going to be the eigenvalues of C, and so on and so forth, right? So that's how you relate this idea of principal component analysis to eigenvalues and eigenvectors, which is kind of what I was getting at when looking at these plots here, right? You think entirely in terms of the eigenvalues and the eigenvectors. Right, and I should also say, we know C is equal to X transpose times X. So this also, it's the diagonalization. It's also the singular value decomposition based on what C is, but you don't have to care about that. Right, so this is the idea here. Any questions about how we got here? Okay. Yeah, so this is the idea. There's like some details I kind of skipped out on. There should be like a 1 over n minus 1 that shows up, but it's just a scalar, so it doesn't really influence the calculations all that much. But yeah, so this is the idea, right? So we've discovered that the solution to principal component analysis is to just perform the diagonalization of the data covariance matrix. And so these eigenvectors are going to be the weights for the data variables, and their corresponding eigenvalues are going to be the variances of the data along each direction. Which might be like impossible to visualize because usually these are really big data sets. And then what else do we want to say? This is kind of what I was getting at before. Like these covariance matrices are really X transpose times X. So we know they're going to be symmetric. So we know the eigenvalues are going to be real numbers, and we know that their eigenvectors are going to be orthogonal as well. And so that's really the main theory here. So I'm going to go through a couple of examples. I'm going to continue talking about kind of like this Turkish stock market example. And then we'll also look at eigenfaces as well. And so before going over the code, I wrote like the algorithm out for principal component analysis, as well as kind of what it's telling you, what it's doing. So the step or to perform principal component analysis, there's kind of these 5 steps here. Maybe not all of them are necessary, but the main idea is you compute the covariance matrix of the data. You take the eigen decomposition of that covariance matrix. And then this isn't what we did in class, but you should be doing it if you're performing principal component analysis. You should be ordering the eigenvalues from largest to smallest, because the largest eigenvalues are the most important. They have the most influence in determining or understanding your data set. So people will sort the eigenvalues descending by magnitude. There's some terminology associated to it that I'm not going to use. There's this idea of like the various component scores, which is really just looking at how much each value of your eigenvector is contributing to that eigenvector. And then usually you convert the eigenvalues to percent variance in order to make it so it's easier to interpret what's going on. Right, so I'm going to demonstrate all of this, I guess, in the code that I have here. I'm not going to go through like every little detail, and I can't really capture this via recording. So people are watching this lecture on YouTube, I guess later on, you can't really see what's happening, but I'll be posting this on Canvas, like the PDF on Canvas. I think it's just adjusting, or maybe it's just not. It'd be sad if it's give me 1 second here. Maybe if I turn them off and then turn them back on. Yeah, because all I did was change the display. Might just be the HDMI. Wait, maybe if I'm gonna unplug it and plug it back in, and if it doesn't work, we'll just move on to 8.1 and then I'll go through the example on Friday. But we'll see. It was working the other day. I don't know why it wouldn't be working now. I guess the alternative, I don't know how long this would take. I could log into the Zoom on my tablet and then just share screen on my computer or something like that. I'm gonna give that a shot.
Are you sure the screen here?
It should be. I think the issue is it doesn't seem like it's detecting the HDMI cord. It's like the HDMI cord is plugged in. Like all the screens are on, and it says like it is the laptop. So like the issue is just going from the room PC to the laptop. Yeah, I don't know. Well, I'm gonna try. I don't know. I don't think it should take too long. I do want to go through this now just because I like doing everything in like the correct sequence, I guess. So I'm gonna try. I'm just gonna join the Zoom meeting that this is currently on, and then I'm just gonna share screen. And I think that should be fine. And I don't think it'll take very long to do this. This is 537-915. Yeah, this is why I don't like. I mean, it's nice to just use the tablet. And in math classes, you don't have to usually do this kind of thing. Okay, and then I just need to be able to share.
Are you gonna release the homework 8?
Yeah, I will. That'll be today. Just because yeah. There it is. Okay. That kind of worked. Okay. Yeah, so this is what I was talking about. It'll be a little bit laggy because it's not HDMI, it's on the Zoom. But anyways, this is what I was talking about a little bit on Monday, right? So this first cell here, this is again like this Python page. I'll do like a PDF, put it on Canvas later on. So this is like taking in data regarding the Turkish stock exchange as well as other markets as well, like financial markets. And so it ends up being 9-dimensional. There's going to be 9 markets we take into consideration in total. And so I'll say a little bit more about it now. This first cell here, is this putting in packages that will allow us to do linear algebra as well as plot pretty much. This cell here, I talked about it a little bit in class on Monday. But what we were doing here was we were reading in the actual Excel sheet. And then we read it into a matrix via this for loop that we have here. And then we computed the covariance matrix. So again, this covariance matrix is just taking your data matrix, finding the transpose, and then multiplying it by the data matrix. And then you divide by like the length of the data to normalize it. And then you can find correlation as well by just scaling the covariance matrix. So I went over this in class on Monday. There's some display options down here you don't have to care about. And so what I ended up plotting initially is just the covariance and the correlation. So I said a little bit about this already, and they're pretty large figures, but with the covariance matrix, these two plots are pretty much the exact same thing, except the correlation matrix on the right here. It's normalized between -1 and 1. So as I said before, like this DAX and the FTSE, they correspond to, I think, Britain and Germany, or perhaps the opposite, like the flip of that. And so there should be a high correlation between what's going on with the EU and what's going on with Germany and the UK as well. Like it shouldn't be too surprising. And so this is the correlation that exists between all of the different stocks we're looking at or markets we're looking at. And then in terms of reading in the data, so this is all the, I guess, all of the markets on top of one another. It's incredibly noisy and kind of hard to see what's going on because there's, again, 9 total markets that we're looking at the moment. And so the purpose of principal component analysis is to reduce this 9-dimensional data set into something that's just going to be 1 or 2-dimensional. And so as we saw in class today, that to perform principal component analysis, what we're really doing is we're just doing this diagonalization process that we've already learned about in chapter 6, right? So this whole cell here is doing that process. So you can use, this is like I'm using NumPy or NumPy, I don't know how to pronounce it, on Python. I think it's NumPy probably because it's like Python. And so you can use it to calculate what the eigenvalues and eigenvectors are going to be. Here, like NP, like eigenvalues here. And then what I do is I sort the eigenvalues and the eigenvectors from largest to smallest. There's like some trickery involved here a little bit. And then it's talking about the component scores as well. So when I'm talking about the components, again, I said this in class on Monday, but the components really just correspond to the eigenvectors that you have. So the number of components is equal to the number of eigenvectors and really the same as the number of eigenvalues. And then what we do is we perform, so this is the diagonalization part. And so I'm just looking at the first 2 components at the moment. And so I'm looking at the first 2 components. It's taking the original, I guess, concatenation or composition of time series that we have, and then distilling it down into these 2 time series that take into account all the variables that we have. And so you can see, if you look at component, it's labeled component 0. So this is corresponding to the largest eigenvalue that you have. So it's the most influential. And then component 1 is the second largest. And you can see that component 0 takes into account more of the extremes that show up within the data that we had. So we kind of like have this huge spike here in component 0, which kind of corresponds to this huge spike right here. And so this component is taking into account like the greater amount of variance that we have, right? Compared to component 1, which is kind of compressed a little bit more. It doesn't have the like as high of like an amplitude or something like that. Oh yeah, and I have like some text written down here that I kind of already explained. So like a component and principal component analysis is just a linear combination of original features in the data set that are eventually represented as eigenvectors. So there's a couple of plots. I'm going to skip this part here and just go down to the bottom. And so by using the eigenvectors and the eigenvalues, you can determine really, so I'm not going to use the word like true dimension, but like really what's influential in understanding the original data set that we had. And it's all kind of represented in this scree plot that we have here. It's like what this scree plot is saying is that we're going to have 9 eigenvalues, but it's really just, I mean, maybe it's up for debate, but it's really just this first eigenvalue that has like a significant amount of influence to it. And so if I were to cut out all these other eigenvalues and all of these other components, like this single eigenvalue and the corresponding eigenvector would represent about like guesstimating like 65% of the data, right? So I'm going from 9 dimensions to 1 dimension, we're still retaining like 65% of the information. And then the data down here, so when it's talking about weights for a component 0, this is saying like we have the most influential eigenvector, and then we're looking at the numbers that make up the eigenvector, and we're seeing it's mostly like the ISE and like this ISE1 that are contributing the most to the direction that that eigenvector is going to end up pointing into, right? And you should see these numbers are generally larger than the ones we have in component 1. So like to summarize, and you can look into more detail on this. I'm not going to, this isn't like a data science class, so this is just kind of like a quick example, and then we'll look at eigenfaces and move on pretty much. But this summarizes what's going on down here, kind of in ways that I were already saying before, right? So there's really, from the scree plot, you can determine there's one large component that accounts for about 64% of the variance in the data, while all the other components account for 15%. Or less. That's like this scree plot right here. That's what it's telling us. And so from the perspective, I'm pretty much just reading this off, but from the perspective of dimensionality reduction, we can reduce the entire data set to the component associated to the largest eigenvalue, called the top component, which then reduces the 9-dimensional data set into like a 1-dimensional vector. And in doing this, we lose 60% of the info in the data set if we only focus on the top component. But the important features are probably going to be captured within like this 1-dimensional vector instead of, or like this single vector, rather than having like some noise that might be misleading within like the entire 9-dimensional data set. So sometimes losing pieces of the data can actually be somewhat beneficial in that you can be losing random noise. You'll be ignoring that random noise. Right, so that's just like a quick example. At the end of the day, we're not doing anything aside from just looking at eigenvalues and eigenvectors. So maybe it looks a little more complicated because we haven't looked at like scree plots or anything like that, but all of the work and all the stuff that we're doing is really just this part right here. So it's finding the covariance matrix and then just doing diagonalization, and you get this really powerful information. So it's quite nice. And then I also wanted to say a little bit about eigenfaces as well. I kind of want to go back to the tablet first. This is kind of annoying going back and forth between the two, but 1 second. Oh, I ended this, whatever, it doesn't matter. Okay. Yeah, so saying a little bit about eigenfaces before going into the sample code that I have and demonstrating it. And so first, I guess before going into eigenfaces, I want to say a little bit about how like matrices are used to represent images. And so I think I was saying it in the beginning of the semester that linear algebra is probably the most important area of math in the modern world. And that like pretty much everything you see on the computer, like all digital images, all of those things like image manipulation, like videos, stuff like that, can be expressed as a sort of matrix. And so I'm going to represent it, or at least demonstrate this in one of the more simple examples where you have a black and white image. And so if you have a black and white image or like a grayscale image, it can be represented as a single 2-dimensional matrix, or like a 2D matrix, meaning that you just have rows and columns. If you have something that's in terms of like red, blue, and green, like a colored picture, then you actually need to use like a tensor. So like there'll be pigments associated with green, that'll be represented by a single matrix. And then if you wanted to do like blue and red, like each of those colors would have a corresponding matrix as well. So you have like a tensor of matrices, which we haven't really talked about, and it's kind of outside the scope of this class. But if you're in black and white, you can represent an image as a matrix where the number 0 represents that you're having the color black, and at the value of 255, you're getting the color white. And so if you have this initial image and you broke it down into, this would be a really low resolution picture. So we're using a small number of pixels here to represent this image. So here, this is like something that's getting close to black. And so you have like the value of 81. Here's like you pretty much have white. So you have a value of like 249, which means it's almost white. And so if you have more pixels, it means you have larger matrices. So you need like larger matrices and thus more computation in order to work with higher resolution images. So that's kind of the idea that's being explored in Eigenfaces a little bit. And that this idea behind Eigenfaces is it's going to be using principal component analysis to take a picture of a person or a person's face, which can have like, which could be like something that's like 2 million dimensional or something if it's like a really big picture or something. And then it's going to reduce it into lower resolution images using singular value decomposition. And then from there, it's going to take the components that matter the most and being able to recognize someone's face. And then it's going to disregard everything else. So we're going to look at eigenfaces. This is a term first introduced by Serovich and Kirby in 1987. So as I was kind of saying in class on Monday, it's probably like something that doesn't really have like a positive connotation at all, but like eigenface is the fundamental concept used for facial recognition. This is kind of like a dated way of doing things for, I guess, like picture recognition. There's like convolutional neural networks now, which are a lot stronger and being able to do like image recognition and like digital view or whatever. But I think this was used, at least from what I read online, I think they used eigenfaces in like the 2005 Super Bowl or something like that to keep track of like who was attending. So this is kind of like dated, and it's also going to be dated when you look at the data set I'm using. It's going to be like George W. Bush and like Tony Blair and stuff like that. So this was like things that people use in like the 2000s, but now there's more sophisticated means of doing it via neural networks and convolutional neural networks. But at its core, eigenfaces is a set of feature basis obtained by applying principal component analysis, building on singular value decomposition. And as I said before, it's really projecting these higher dimensional face image spaces to a lower dimension, make it so you can take in a larger set of them and actually manipulate them without it taking too long for you to go through with the operations. And so in the real life scenario, person's face can have millions of pixels with the development of photographic equipment, but you don't want to work in a 2 million dimensional vector space. Like you want to reduce the number of dimensions you're working in as much as possible. And so the main idea, I don't know if I want to read all this text out, but the main idea is you take a higher resolution picture, you apply singular value decomposition, and then you look at the number of components you need to start to understand like or to actually have like effective facial recognition, right? So like this is like the original picture that someone has. Applying singular value decomposition, this is when you use the first 20 eigenvectors to reconstruct the picture. This is when you use the first 100 eigenvectors. This is when you do the first 200, 400, 800, 1,000. And you can keep on going. There's like tens of thousands of eigenvectors you could use. But what you should kind of notice is that you kind of get the image or like the key facial features of this person's face at around when you have like 400 to 800 eigenvectors. So instead of using like all tens of thousands of eigenvectors and eigenvalues to reconstruct this space, it seems sufficient to just use like the first 400 or 800 instead. And so that's kind of represented by this singular value plot that we have at the bottom. So again, these singular values are just the square roots of the eigenvalues that we have. And you can see there's kind of a massive drop off in terms of how influential the singular values are as you descend in value. So like this goes on to like thousands and thousands. This is like a 32,256 dimensional vector space. So that's how many singular values you're going to end up having. But it seems like you only need to consider like this many, or maybe even less than that, like maybe like this many or so. And so like these singular values are going to capture the most important parts of your face, like your eyes, your nose, like your chin, stuff like that. And these smaller singular values probably correspond to like having like an indistinguishable wrinkle or something like that. Something that's not really like that important in determining someone's appearance. And so just to show you an example of this, I'm going to share my screen again for the laptop and hopefully it's seamless. Yeah, so just as a quick demonstration of this, this one I'm not going to say as much about because in this algorithm, we're actually using some things from scikit-learning, some like algorithms from machine learning that we haven't really discussed. And it's kind of outside the scope of this class. But it is illustrating the main ideas of this principal component analysis and singular value decomposition in ways that are visually intuitive. So a lot of this is just reading in data sets, splitting up the data set into like training and testing data sets, and then you have like your X and your Y, where these are like your predictions. So you don't have to know really what's going on here. This cell is dedicated to looking at or applying principal component analysis to the eigenface data sets or data set. And then this is like mostly focusing on visualizing. So down here, so like what this is doing is we're reading in a bunch of images of, in this case, various politicians from the 2000s, I suppose. Some of these names I don't really recognize, but you have like George W. Bush, Hugo Chavez, Tony Blair. And so that's like what we're reading into the data set. And again, all these pictures are just matrices at the end of the day. And then we're performing some sort of training on, in this case, it's like SVC. So it's like support vector classification. And it's trying to guess. So it'll read an image. And what it wants to be able to do is it wants to be able to guess who that image is of. And so that's kind of represented its success over here. And that what it's saying here is that it's giving, like, it gives you some sort of picture. It gives you a picture of like George W. Bush or something like that. And then the computer, the program needs to be able to guess that it's George W. Bush. And so this records all of the guesses that it has for all pictures of George W. Bush. So for the most part, if it gives you a picture of George W. Bush, it recognizes that it's a picture of George W. Bush. I don't know like the exact number here, but it's like 145. It guesses it right 134 of the 145 pictures it has. Sometimes it guesses it's like Tony Blair. It did that once. Hugo Chavez once. These other people like 1, 2, 3 times. So this is really just recording the success and accuracy. And you have like particular numbers represented up here where it's measuring the precision. So it's like it was able to guess it was George W. Bush correctly 94% of the time. Others, it was less successful. And so kind of what it's doing, again, like it'll give you these pictures, again, these kind of like really dated pictures, but so like it'll give you these pictures and then it's going to be reducing these pictures into like the most important components, which is kind of creepy when you actually look at what it's looking at. So like these are the original images that it's looking at, but down here is what it's actually looking at. Just like these ghostly kind of scary faces that you would see in like a, I don't know, some sort of like horror video on YouTube or something. But like it looks like a skull almost. But like this is what it's actually looking at. You can kind of see like this is kind of like George W. Bush probably, but it's really just capturing like the eyes and like the nose and like the agape mouth, I guess, which is I don't know, probably his mouth open more than other politicians, I guess. But from this, it's able to determine like who these people are pretty much, right? So if you look at like what it's doing, like it looks at this image and it predicts that it's going to be Bush, and it ended up being true. Same for these other images as well. So like a picture of Tony Blair. When I was like in 6th grade, so I'm like older than I look maybe, but when I was in 6th grade, I think my teacher said she had a crush on Tony Blair. So it's like 20 years ago or so. So that's what he looks like in case you're curious. His name's Schroeder, but he looks very German to me. Powell, I don't know who Powell. Oh, Colin Powell. He's like I don't know much about him, but yeah, this is kind of the idea of what's going on. So like it's guessing on these faces based on these kind of spooky images here. So these would be like only using maybe like I don't know how many eigenvectors were used necessarily, but instead of doing like thousands of eigenvectors, they're using maybe like 100 or 200 here, and from that they're able to tell like which person is which. That's the main idea. I don't know if I really have that much more time. Maybe I can say a little bit about linear transformations a little bit. And we only have like a couple of minutes, but maybe I can just go through like the definition, I guess. Oh, that was nice. Yes, that's kind of what's going on with the principal component analysis. I can't really ask you questions on the exam where I tell you to do like eigenfaces or anything like that, but there could be like a conceptual problem, I guess, where I'm like, what does principal component analysis I do pretty much? In which case you can say it's like dimension reduction and stuff like that. I don't know exactly what your answer would look like, but it is something I could ask on the exam. I'm not going to ask like programming problems on the exam, obviously, though, because we haven't learned any Python. Yeah, we'll look at other applications next week. I do want to maybe look a little bit about into like machine learning. Like machine learning is really like matrix. It's really just matrix multiplication at the end of the day. So we can talk about that. Yeah.
Are we going over like the principles of kind of transform?
Well, I don't know. Well, I don't know I don't even know what I'm talking about next week, to be honest. Like I'm going to talk a little bit about linear transformations because that's like, if you took a linear algebra class, you have to know what those are pretty much. That'll probably be like Friday and Monday. And then on Wednesday and Friday, I don't know yet. I might do like Markov matrices, or I could do like neural networks or something like that. It won't take too long. Let's see. Actually, I'm probably just gonna stop here. I mean, I usually stop class at 12:47. It's 12:46 now. So let's do this on Friday. I might have like a shorter quiz on Friday or something like that, but I do need to talk about transformations. Well, you and your class. Yeah. Nah, shout out to I might have like if it wasn't for Jacob, bro, I wouldn't be able to classify. Yeah, yeah.